All right, hi everybody. Today we're going to take a brief break from the textbook material and we're going to look at a journal article that comes up with a new model for cumulative damage, and it's based upon all of these concepts that we've been learning. And the reason that we're doing this is multiple, but the first reason is that the material we're actually learning in the textbook comes from these types of journal articles that were published in the 1960s through kind of the 1980s. And so there have been some important works that have happened since then, but you get to see where the book content comes from and why it comes from these kind of journal articles. So I'll talk a little bit about just what are journal articles, where do they come from, how do they get published, and things like that for those of you that don't live in the world of academia. So that's what I'm going to talk about quite a bit today. And also, we're going to go through this because I want you to see how those concepts are used so that at the end of the term, I'm going to ask you to review a journal article. And I'm going to ask you to come up with the ways at which this journal article aligns with what we've learned in the class so far, whether it's based in the same sort of approaches, foundational principles, or whether they've taken a different approach and why they've taken a different approach. And so don't worry about that too much now, but I'll provide a small bank of articles that you can choose from, or you can choose your own article to critique sort of near the end of the semester to kind of just synthesize what we've learned. Okay, so today I chose an article, and this is a sort of a picture of, if you're reading the article, this is at the top. And so I'm just going to go through a few things. So you can see that this article is published in the International Journal of Fatigue. Okay, so this is a journal made up of maybe a head editor and then an editorial board of researchers from all over the world, most of whom are in academia, but some of whom are in national research centers or private industry, but for the most part they're going to be from academia. And so I'll tell you why that's important in a few minutes. It's published by Elsevier, this journal is. There are many journals published by this particular publisher. And this journal is a subscription model journal, which means that universities or other government entities, et cetera, will buy a subscription to be able to get issues, read issues of the journal, and that's how they make their money. So the people who publish in this journal do not pay the publisher to publish. There are some other journals that are more open source, and they have a different funding model in which there is an article publication fee that the authors of the article actually pay such that it can be published and then read by anyone. There's no subscription necessary. There are pluses and minuses to both of those types of publication models. This one happens to be International Journal of Fatigue, and UF subscribes to this journal, so we as students and faculty have access to it for free. And so you can go to the library and click on a link and it will take you right to this article or any article. The title of this article is Nonlinear Incremental Fatigue Damage Calculation for Multi-Axial Non-Proportional Histories. Okay? So there's a lot of adjectives in here, but if we sort it out, it's based on the fundamental things that we've been learning. So this is the main noun in the article title, fatigue damage calculation, and they're going to talk about an incremental fatigue damage calculation, right? So we have also been talking about incremental cumulative damage models, but they're going to be talking about one that's nonlinear, okay? So we had like a single linear damage accumulation model and then the double linear one, but this is saying that we're just going to throw out the linear portion completely and assume that everything is nonlinear. And then they're going to apply it to a complex situation, which is multi-axial, non-proportional histories. So that means the stress history, the loading spectrum history. And so we'll see what they do with that. This is an article that is a result of a collaboration between people from two different universities. And so you can see that the first author is notated with a little letter A, which shows they're from a Department of Mechanical Engineering in Brazil. And then The star means that they're the corresponding author, so they sent all the documentation back and forth. The second name is also an A, and the third name is Institution B, which is School of Aerospace Engineering and Applied Mechanics, Tongji University in Shanghai, China. And so these people work together from across the world. My guess is that some of these people did the more theoretical modeling parts of the paper, and then the other group did the experimental part of the paper. And then they validate each other, and so they publish the article together because it strengthens the work of both parties. Excuse me. So the order of the authors on a journal paper is specifically chosen such that the authors at the end of the article are the more influential authors or the ones that supported the work through research funding. And so if you were to look up these last two authors, one from each institution, you might find that those are the professors, or those are a postdoc, or someone with more experience. And then usually the first author on a paper is the person who did either most of the work or wrote the paper. And those roles can change a little bit, but that's typically how it's done in these kind of subscription model journals. And so if you're looking at doing some research in a graduate school, or you want to know, like, who was the professor in charge of this work, you look at the last author, and that's going to be a good hint. So that's the person that you would look up, and then you could look up other papers by them and see what their body of work is. The first author may be a PhD student, master's student, researcher of some kind, and so they may or may not be continuing on in academia. They may or may not become sort of the primary investigator, the PI, a professor, but they did the most of this work. They were the hands doing the work and the coming up with the computational results and so forth. So this is kind of the cover of the journal article. It tells us generally what it's about, who wrote it, where they're from, where it's published. And so the next thing I want to show you is just, it says article info. So it gives us article history, when it was received, when it was accepted, when it's available online, and then what the keywords are that we will know that this work is around. So the article history says it was received on middle of September 2016, and then it was received in revised form November 2016, accepted on the 3rd of December, and then available online shortly after that. And so I want you to just take a little bit of time here to understand that this is how we know, we come to believe in different theories or prove different things that are then put in textbooks, and we learn about them and we use them to design things in the real world, is because of this publication and peer review process. So when it says the article was received in September, at that point an associate editor will identify 3 or more reviewers unknown to the authors, and those reviewers will be asked to critique the article, and they will be subject area experts in this field, and they'll be asked to comment on things like, do the conclusions follow from the results? Is the background well researched? Are the methods appropriate? Does the data make sense? And so they're asked to give an advisory report on many different aspects of the paper. Usually there are 3 or more of these kinds of reviewers, and all of the reviews are collected by the associate editor, and they sort of synthesize out the information. And they say, okay, based on all of these reviews, I would either accept the article as is, like it's a great article, no changes requested, or the reviewers have come up with a few points that really need to be addressed, and maybe some edits made to the article before it's published, or there could even be heavy revisions required, or it could be rejected if the reviewers are very negative about its scientific contribution. And so the peer review process is quite important to the publication process, and knowing what we know and believing what we believe about the physical world. So I want just to make sure that you knew about what that process is. The keywords of this paper, as provided by the authors: multi-axial fatigue, variable amplitude load, non-proportional multi-axial load, nested fatigue damage surface, incremental damage calculation. So these are very specific keywords. They've gone for not very general, but that's because this is published in International Journal of Fatigue. So most of the readers of this journal, most of the readers of this article are going to be familiar with a lot of these concepts already. So I'm going to put some words up now, but I'm going to go through it. I'm going to highlight some of the most important things that I want you to recognize. So this is an abstract. It's usually 150 to 300 words that give an overview of what the paper is going to tell us. And so it's kind of a snapshot of the paper. So the abstract is very important to read, and it can tell you what kind of stuff you're going to find in the paper. Are you going to find experiments? Are you going to find computation? Are you going to find analysis? Are you going to find new uses of old approaches? Are you going to find new approaches? Right? So it really helps to sort all of that out. So this abstract, as most abstracts do, starts with a general introduction, right? And the general introduction is about fatigue models. It says somehow fatigue models must somehow identify and count individual load events before quantifying the damage induced by each one of them, making multi-axial fatigue damage calculations under non-proportional loadings a challenging and laborious task in practical applications. Moreover, right, so compounding that complication, to apply such models is usually necessary to use semi-empirical models to evaluate the non-proportionality of the load path of each event through path equivalent ranges using other specific methods. To avoid this burden, all right, so this is what these authors are contributing here. A new approach called the incremental fatigue damage methodology is proposed. So that means it's here in this paper. To continuously accumulate multi-axial fatigue damage under actual service loads without requiring path equivalent range estimators or rain flow counters, okay? So they are not looking at a stress amplitude or a strain amplitude and implementing an algorithm to do counting of all of those different loading cycles. And they say this new approach is not based on questionable continuum damage mechanics. So they're getting a little spicy here. Apparently they feel as though continuum damage mechanics is not very accurate and should not be used. Or on the integration of some unrealistic scalar damage parameter based on elastoplastic work. Okay, so that would be another approach, is to say that fatigue damage accumulates because of work that's put into the material, right? So there are some models that said that. And these authors believe that those are unrealistic, so hopefully they'll have some evidence for that later in the paper. Instead, they say, inspired on multi-axial plasticity procedures, a framework of nested damage surfaces is introduced, allowing the calculation of fatigue damage even for general 6D multi-axial load histories. I'll tell you what that means in a minute. And in this way, fatigue damage can be continuously integrated along the load path, considering damage parameters adopted by traditional fatigue models and following reliable procedures well tested in engineering practice. The proposed approach is experimentally validated by non-proportional tension torsion tests on tubular 316L stainless steel specimens. And so I want to go back, and so they say that it allows for calculation of fatigue damage for 6D multi-axial load histories. So you might think, okay, I understand up to 3D, maybe 4D if there's time involved, but 6D, what does that mean? In this case, it means the different, let's say, facets of damage. So they're going to call those damage surfaces. And what it is basically like a state variable that defines damage at some time in this model. So it's not truly like a six-dimensional, space or something like that. It's just, that's how they describe this state variable and how many parameters are in it that they carry along that are then used to calculate this accumulated damage. So I'm going to jump to the end of the paper first, because that's my favorite and I can do it, and show you how they validated this work experimentally. So they take a tubular specimen, and so you can see the typical sort of dog bone, but it's symmetric around the circumference, mounted in a tension torsion fatigue testing machine. So this machine has this sample mounted in 2 chucks on the top and bottom, right, that you can see that have some bolt holes in them. And then behind one of these chucks is an actuator. And so that actuator, in this case, is going to provide tension and torsion. So it's going to extend the sample or compress it, and then also superimpose torsion on top of that. And then what's shown here is these 2 little prongs coming out. And these are the extensometer. Okay? So they don't contribute to the load that's felt on this because the loads applied are much higher. But what it does is it measures the distance between those 2 points in space. And so that is a very precise extensometer that can fit onto the load frame and continuously take data at the same time as the force data is being recorded. So they validate this in a really fun way. They come up with combined loadings that apply tension and also torsion. And so if you look up at the top left here, you can see that I pulled from another paper, one from the International Journal of Pressure Vessels and Piping, which shows the superposition of different types of, in this case, strains onto a tension sample. So you can see at the left side here that strain versus time is just in the axial dimension. We know that. And then you could have multi-axial loading where in the second frame here, you have a shear strain versus time on the bottom, right? So that's going to be a rotational strain applied to the sample. And then when you put those together, I'll sort of circle this in light blue. When you put those loadings together, you have the combined tensile and torsion fatigue test. And you can see that I pulled this paper because it has this really nice plot on the bottom that shows the normal strain and the shear strain, gamma, are aligned in time. So they both hit a maximum in time. And so that's going to be important because of all the crazy shapes that this paper I'm presenting to you applies to this specimen. So they have a tubular specimen, and they want to apply enough different types of loading to really demonstrate that their new technique is appropriate and can predict failure. So this is figure 6 from the paper, and the caption says applied periodic epsilon x, so that's the normal strain along the axis, times or crossed with the shear strain xy divided by square root 3, strain paths on an 8 tension torsion tubular specimens. So they've done 8 different patterns, is what they're saying, all of them with normal and effective shear amplitudes 0.6%. So they matched the strain amplitudes in shear and the normal direction to be 0.6%. So when you think 0.6%, you should immediately say, oh, that has a plastic component to that. Because normally when we define the yield stress on a stress-strain curve, we only go to 0.2% of strain. We draw a line, and that's where we say we calculate the yield strength. And so these go up to 0.6%. So they should have an elastic component to the strain, but also a plastic component to the strain. And you can see that these different shapes have different features, right? So one is a circle with no hard corners, right? So no extremes. But then there's also a triangle, multiple triangles, and then this shape at the bottom here, which is sort of, they're just like, let's combine everything that we have already done to kind of create like a most extreme loading history case. And so when they did that, this is the sort of the grand finale of the paper, this table 2. So it's the predicted and observed lives in number of blocks for each applied path. So they define a block as some number of loadings, and then they predict, based on their new model, how many blocks it's going to last. And then they do the experiment, and they note how many cycles or blocks it was able to sustain before a surface crack was observed. That's their criterion that they specifically state in the paper. And then they do like a very quick calculation of what's the percent error, okay? And they were very encouraged by these results. So this just tells you that the stochastic nature of fatigue testing generally means that even if you have errors of 30 or 40%, in general, if you say the trends align, then you can say that this is a valid way of going about things. So just briefly to summarize their results, the cross pattern here that they made, they predicted that would have almost the same and long life, just like the diamond shape here of 13 or 1400 blocks. And then they observed that the cross pattern could withstand 1500 and the diamond pattern about 1000. And so they were in the correct order of magnitude with errors of the cross pattern of 14% and the diamond pattern of almost 50%. As they go more extreme in loading, the number of blocks in the lifetime of these specimens went down. So triangle 1, triangle 2, circle, square, etc., down to that super combined loading, where they predicted it would last only 327 blocks, and it lasted 288. So they seem to have a better, maybe slightly better correlation between the predicted life and the observed life at these extremes, but they did have one that they hit pretty closely there in the middle as well. The other ones all range kind of 20 to 40, maybe more percent error, but in general, the trends align, right? And so I want to also point out that these authors chose not to put a plot in here of what the predicted versus observed was, and I don't fault them for that. But in my mind, I would assess, or I would assign some sort of like a extreme damage parameter to these different shapes. Like how extreme really is it? And then you could say that that the predicted life was like this and the observed life was like this, and you could show the plots, and that would be a more visual representation. But they've chosen to put it in a table here. And I think, I can't get inside of their heads as to why they might have done that, but just taking into consideration the stochastic nature of a lot of these measurements, sometimes they look a lot worse on a plot, and so sometimes the data is much better handled in like a table format. Also, if they put it on a plot, sometimes they don't provide the numbers. Here they've actually given us the numbers, so that's awesome. So we could go and make plots. We could do the same type of prediction they did and see if we get the same numbers. And so providing these tables is also very helpful in that sense. Okay, so how do they contextualize this problem, and why are they studying it? Why do they think this is important? Well, they lay all of that argument out in the introduction. And normally this is an academic motivation that's presented here. It's not like, there was some sort of engineering failure that we are trying to understand or trying to overcome, but rather they're saying a lot of models for multi-axial, what do they call it, non-reversing fatigue histories don't have great models for them already. Or if they do, they're very tedious, like adding up the damage accumulation for each cycle, and it becomes too computationally expensive in terms of HR time, like personnel time and resources for the benefit that you get from those predictions. So they're saying let's think about it a different way. But they have to describe to the reader what is the state of the art in the field. Where are we today? And make the argument for why it's insufficient, why there's a knowledge gap that needs to be filled, and then what they're doing to fill that knowledge gap. And so they do that usually by starting out very generally at the beginning of the introduction. So this first paragraph of the introduction is understandable by everyone taking this class. So I'm just going to read it very briefly, underline some keywords. Macroscopically speaking, okay, so not at the micro scale level, fatigue damage can be regarded as a continuous process caused in real time by cyclic elastoplastic straining, usually localized in a single point of the structural component. To quantify such a process, most fatigue crack initiation models need to identify individual load cycles to compute the damage induced at that critical point by each one of them. In this way, such models require knowledge of the whole loading sequence to assess the damage induced by the current event, right? So they are discrete in nature, since they can accumulate fatigue damage D only after a full cycle or half cycle is identified. That is, detected from a load reversal or from a hysteresis loop that closes. So that was the basis of our rain flow counting, was that we wanted to close the loop on all of these strain cycles and have a full forward and back, or at least a half cycle, that we could say, oh, the maximum strain was this, the minimum was this, the mean was this, and quantify such state, and then add some damage on based on that state. And so this paper is setting us up that this discrete model is too time intensive and not good enough. And so you can sort of read ahead from this that they are going to present to us a model that's not discrete, right? A model that's continuous. And so then they go into specifically why these things are challenging. So this is just paragraph by paragraph. I'm not going to do them all. But they will funnel down. They'll start with a big problem. Then they'll funnel down into details that specify the exact problem they're going to address in this paper. And a good paper introduction is able to capture the reader's interest, tell people where they're starting, what their starting point is. So that's what this first paragraph is. And then to funnel down in a logical way that everybody can follow what they're going to do in this paper. The introduction is the hardest section of any paper to write, and I usually recommend that people write it after they write the rest of the paper, such that they can appropriately contextualize their findings, the problem, all of those things. Okay, so now they're going to go into a little bit more detail, right? They said that identifying cycles was pretty intensive. So now they're going to say cycle identification under variable amplitude loading is not a major problem under uniaxial load histories, right? Since the rain flow method is an appropriate and sufficient cycle counting algorithm in this case. But cycle detection and counting can be quite challenging task under multi-axial non-proportional histories. So NP, what does that mean? Non-proportional history, where peaks and valleys of each stress or strain component in general do not coincide with the peaks and valleys of the other components. In this case, it's impossible to decide a priori, that means sort of before you've seen all the data, which points should be considered as load reversals for cycle detection. So imagine a multi-axial loading, right? And then it's hard to look at the combined loading and say which points count as a load reversal. It's like if you did two rain flows on two different principal directions, and then you tried to put those rain flows together and see how they lined up. They often don't. And so this is what they're stating here. And so they talk about a simplistic approach, rain flow counting, and then they talk about how a number of multi-axial rain flow algorithms have been proposed. So they're either based on cycle counting of von Mises equivalent stresses, right? So you could take your principal stresses, combine them into a parameter like the von Mises stress, and then do the rain flow counting, right? Or strains. So you can do that by combining all of the principal strains. And then these models were engendered by these particular people, right? The Wang-Brown, or path-dependent multi-axial flow. Right, so they start going into very specific papers that they've read, right? It gives other references here where other people have described these techniques. And then they also have to identify why those techniques are still insufficient to account the problem that they're trying to solve. So they'll use words and say, these approaches, unfortunately, do not take into account these kind of effects, right? And so they're trying to say specifically why these methods are maybe insufficient. Okay, And then they continue on, right? I'm not going to read all of this text, but it says, moreover, the existing multi-axial rainflow algorithms are neither very robust nor consistent, since they can output very different half cycles depending on the choice of the initial counting point of a periodic loading history. And so they're saying that, yes, there are these multi-axial rainflow models, but apparently you get very different results whether where you start that first rainflow. So it can be a problem for prediction, right? And so they say, sort of in the middle of the introduction here, that a completely different calculation approach is followed in this work. Assuming fatigue damage is a continuous variable, whose increments can be computed as the loading proceeds. Fatigue damage is continuously calculated after each infinitesimal stress or strain increment. Thus, it does not need the identification of load cycles. So in this case, they're saying we're throwing out any type of cycle counting. We're throwing out any type of, background of this whole stress life approach, which is to say, what's the stress and how many cycles can you sustain at that stress, right? So it's kind of a big shift, could be a very big shift in the thinking about the accumulation of fatigue damage. And so they're saying that they don't care about like a full loading cycle to add to the damage. What they're saying is that infinitesimally small stress or strain increments, so even like a portion of a load cycle would count toward the accumulated damage. And then the next little portion of the load cycle, such that infinitesimally small portions of all of these curves would add up into some damage. And so they then go on to develop this model. And they talk about other models as well, because if you're throwing out the cycle model, then you might be going to something that talks about local approaches, right, that talk about just that surface and just that crack. And so they talk about two main types. So one is energy integration approach, and they talked about this as being insufficient in their in the introduction, or they hinted as to that, where the strain energy, either plastic or elastic plastic, or some other energy-based damage parameter, is directly integrated and compared to a critical value. Okay? And so this goes along the same path as a lot of our failure criterion that we've studied, right? So you integrate up something, and then once you reach a critical threshold, then okay, we've had a failure. The second technique they're calling IFD, incremental fatigue damage approach, where fatigue damage itself, instead of an indirect parameter, is integrated until reaching a suitable critical value, right? Something like 1 according to the Miner's rule. And then they go into each of those two approaches. They're going to focus on this IFD approach, which basically is described as the damage, D, of some stress, is defined as the change in stress with respect to that parameter. And then you calculate D based on, or you can say the opposite of that, right? Where you can calculate D based on integrating some stress, some D function as a function of stress, right? Or you can integrate over the stress to get that damage, right? So this is one way that they give sort of a schematic to describe what they're talking about when they talk about these infinitesimally small changes in stress or strain that they are integrating, right? And so if you think back to what you know about springs, or maybe your vibrations class, where you have springs and dampers and all sorts of series and parallels, right? We can even apply that system to the damage state for fatigue damage. And so this figure says uniaxial rheological model. So it can be rheology, which is like the study of fluid mechanics, right? Or fluid flows, but this is also, to me, an analog to electrical circuit models, spring and dashpot models, so it's all kind of similar. For kinematic hardening, with a series of spring slider elements of stiffness H and slider threshold Ri, and resulting stress-strain curve under monotonic tension. So each of these elements has a stiffness, right? So that would be like K if we had our like linear spring F equal Kx, right? That's what they're determining as the stiffness. And then each one of these segments can move, and then each one of those drags a slider here. And the slider is one aspect of the damage accumulation. So that's their conceptual model that they are now moving forward with. And so they have a stress, right, in some dimension, and there can be some elastic strain along that dimension. And that's just represented by a spring with sort of properties E, right? And then when you get into the plastic strain, this epsilon x in the plastic domain, that's where you start to get these unrecoverable changes that contribute to the damage. And so that's how they add up the damage in this model, where the total strain is just the sum of the elastic strain and the plastic strain, and that's why these elements are all in series. So that's a conceptual model for what they're putting together. And so then they come up with an integral, and this case it's a numerical integral, but it says the accumulated damage D, right? And they say it's kind of analogous to accumulated plastic strain, is obtained from the length of the path described by this multi-dimensional damage vector, calculated either in continuous or discrete formulations. So they say that if it's continuous, they're using this integral, right, along some path. And we talked about the J integral being like an arbitrary path. So they're using kind of that understanding. And then so they have the continuous with the integral sign, or in a discrete fashion, right, where we use that capital sigma for a summation. And then at the bottom here is like a few other models that they've had to pull in order to fully do the summation. So they've got some different vectors in here that represent the damage state, and then they have their infinitesimal increment in damage, this little d. M is the number of dimensions of the damage accumulation. And so they sum all of those dimensions, and for a particular stress over some number of cycles, or sorry, not over some number of cycles, but some length of time. And that comes up with this D sigma, this accumulated damage. And so the details of that are not something, it's kind of out of scope of this class, but that's what they have come up with. And then they say, okay, we're going to put in like just something that everyone can understand to show you how this works. So on the left side here, they have a stress damage curve. So, and on the left side here, so it starts at 0, and then it goes up. Normal stress is increasing, and then when we hit the yield strength, we start to have plastic deformation, right? And then the damage is increasing, okay? So they're accumulating damage up to this point. And then the specimen has positive normal stress. Now it's going to have negative. It's going to contract back down. And the damage is not going to accumulate further upon this unloading here. And then some of that damage is going to be undone by going back the other way. And then it's going to cycle back up and do just a positive, negative, fully reversed normal stress. Okay, so that is like sort of a very simple experiment that has one fully reversing cycle, right? And so then they say map out on the right side what that looks like in their accumulated damage model. So the y-axis is that accumulated damage, and then on the x-axis, they say accumulated stress, okay? And so you have to look at the stress over time and how that's being applied. But you can see that they've compared their model, which is the continuous one in gray, to the discrete damage model, which is in the dashed line, right? So in a discrete damage model, you have no damage, so you have a horizontal line. Then you have damage, so you do a step change up, right? And then you add up all these step changes to get the overall damage. Well, in their model, they have continuous damage accumulation, right? So it would go up, and then yes, upon the first unloading, you don't accumulate more damage, but when you get to the very negative stresses, then you do accumulate more damage. And then when you reload, there's an elastic region where you don't accumulate damage, and then there's a plastic region where you accumulate damage. So it's this alternating back and forth in time. When you have increasing and decreasing stresses, you always go back through that elastic regime. And so that's what they're doing here, is basically approximating those step changes as a continuous change. And so they say that the true benefit of this is you don't have to know how many stress cycles that is. You don't care anymore. All you have is incremental changes. So you can imagine that 5 minutes? Okay. You can imagine that if you then put the specimen under significant tension and then in the plastic regime had multiple small amplitude oscillations, that those would continue to accumulate damage, and it would be picked up very specifically by this model. So it's fairly dynamic in that way, versatile. And so the conclusions that they say from this paper, based on all of their analysis and thinking about fundamentally a different way of approaching fatigue damage, and then their validation of that using experiments, is they say this: a continuous multi-axial incremental fatigue damage formulation is proposed in this work based on a direct analogy with incremental plasticity models. Both proposed stress and strain-based approaches can be formulated using traditional stress-strain or other damage models, and then they give a few names, making it attractive and practical tool. In particular, it does not require additional fitting parameters or complex calibration routines, as opposed to equally continuous models that are based on traditional continuum damage mechanics approaches. That's what they called questionable in the introduction. The experimental results show that the proposed method is able to predict quite well, 45% error, quite well, multi-axial fatigue lives under complex tension torsion histories, even though it does not require any cycle detection, multi-axial rain flow counting, or path equivalent range computations. And so the reviewers that got this paper had to assess whether those statements in this conclusion are backed up by all of the work that they did in the paper. And so those reviewers must have said, yes, it does. We believe them. Their approach makes sense, and we recommend that this be published. So I just wanted to share that paper with you today. That's my last slide. And so now you can see how we can look at a paper and look at the important parts and synthesize it down to see what they're doing that is similar to what we've learned, what words we recognize, and what maybe is totally different. And so they, as far as I can tell, this paper did not provide an algorithm or supplementary material such that we could easily replicate this analysis, but that's the trend for more and more journal articles, is to be totally transparent and say, here's my Python code, here's my sets of data, they're published here, and so anyone can take my data and analyze it differently. We're moving into a sort of a phase where the amount of computational tools that we have is exploding, and also we want to make sure that scientists are doing things that we believe in and that the community generally accepts as true, because those are experts in the field. And so providing your data out to other researchers is super valuable and is now being required by some funding agencies. And so I hope that you learned something about journal articles today, how these researchers have used some concepts that we've learned in class and maybe what they're doing a little bit differently, and how they went about this research. So we'll end there for today, and we'll pick back up in Chapter 8 on the next lecture.